Okay, so what we're going to talk about today is this is going to be a quick discussion about what direction fields are and how we go about creating them. So just quickly, just to define what a direction field is, so we can call it direction, or sometimes they even call it a slope field, which they both mean the same thing. So if you're told to find the direction field or the slope field, they're saying the same thing. So when given a differential equation, its direction field is the construction of all of the tangent lines drawn at each point. So what we know is, see, if we go back to the beginning of what we talked about in the school year, is we know that differential equations, which they're the derivatives, that gives us the slope of the tangent line. So what's going to happen as I go to different points, the slopes of my tangent lines are going to change because the point is going to, the x and y values of the points are going to change, which in turn it's going to change the output of my derivative. So what's going to happen is you're just going to see a bunch of lines, and we don't want to draw long tangent lines. It's just small tangent lines, or the slopes of the tangent lines more importantly, and that way what we know is this is one way, and we did this earlier on in the year as well, this is one way of kind of drawing out a sketch of the solution of the differential equation rather than us physically just finding the equation or the solution algebraically. Okay, so let's do an example where we'll see how the direction field and slope fields are drawn, which is very, very straightforward, and then that will basically wrap this up. So for example, if we said sketch the direction field of the differential equation dy dx equals to y over x squared. And see, sure enough, this is my derivative of some function, right? And so what is it that we know about the derivative? The output of dy dx is literally just the slopes of the tangent line at each given point, which the slopes is what we care about when we draw our direction field. So if I come down here and I just draw my coordinate plane, what I'm going to do is we're just going to label some points. Now, obviously, there are infinitely many slopes that we have because there's infinitely many points on the coordinate plane. So we'll pick enough to get a general idea as to what the direction field looks like. So let's go over to x is 1, 2, and 3, and let's go from y is 1, 2, and 3, and then y is -1, -2, -3, and -1. So what I'm going to do is I'm just going to kind of just draw the direction field from in this range of values. So from -3 to 3 as far as my x values are concerned, and then -3 to 3 as far as my y values are concerned. So if we look at my differential equation, see, here's what I know. If I'm on the y-axis, what's my x value on the y-axis? My x value is 0. And what do you notice happens when I plug in 0 in for x here? This becomes undefined, or in other words, what does that mean? If it's undefined, then that means my tangent lines, the slope is vertical, right? It's kind of like an infinite value. So what happens is we know that at x equals 0, 3, 0, 2, 0, 1, 0, 0. Over here we have all vertical tangents. So what you notice is my tangents are all vertical here. So now if I'm on the x-axis, what do we know here? See, on the x-axis my y values are always 0, and what do I notice? With the exception of obviously at x equals 0, because we have a 0 in the denominator here. But when my y value is 0, then what is it that we know here? This becomes the slope of my tangent itself becomes 0, which means I have horizontal slopes. So over here I have a horizontal slope, horizontal slope, horizontal. These are all horizontal slopes. Okay, so notice all I'm doing is what? Just plugging in the x and y values at each given point, and the output of my differential equation, that's the slope of my tangent line. So the other points I care for are where? 1, 1, 2, 1, 3, 1. 1, 2, 2, 2, 3, 2, 1, comma 3, 2, comma 3, 3, comma 3, and then we'll notice that these values are also going to be they're going to be the same, and we'll see why. So I'm just going to label the upper half of the x-axis and find the slopes of the tangents at each point, and then we'll go from there. So for this point, what do we know? X is 1 and y is 1, right? So if I plug in 1 for x and 1 for y, what do I get? I get an output of 1. So the slope of the tangent here is 1. So I'm drawing, notice how at that point I'm just drawing the slope of my tangent, which I'm giving it a slope of roughly 1, all right? And what happens if I go up here? My x is 1, my y is 2 at that point. The coordinates are 1, comma 2. If I plug in 1 for x and 2 for y, what do I notice? The slope becomes 2, right? It's 2 over 1, so it becomes even steeper. So it becomes like that. So this has a slope of 2. And what happens if I plug in a point, or if I use that point? What are the x and y coordinates there? X is 1 and y is 3. So if I plug in 1 for x and 3 for y, the slope becomes, it's 3 over 1, so the slope becomes 3, which is even steeper. So what is it that we're noticing here? When I move up, that's the slope of 1, slope of 2, slope of 3. So you could hopefully see why it's called a direction field, because it's giving me the direction that my curve is traveling. Okay, so we'll kind of get back to that in a minute. So if I go to the left side and do the same thing from -1, 1, -1, 2, -1, 3, what do I notice? I'm going to get the same exact outputs. How come? Because my x is squared. So if x is -1, y is 1, I should still get a slope of 1. If x is -1 and y is 2, I should still get a slope of 2. And if x is -1, y is 3, I should still get a slope of 3, right? Now obviously these slopes are exactly the same because the x is squared. Now if the x wasn't squared, then these would have negative slopes, right? So I'm just literally plugging in the x and y values into my differential equation, and I'm finding the number, and that's telling me what the slope of my tangent is. So if I come over here, if x is 2, y is 1, what do I get? I get 1 over 4, so that's 1/4. So we see that it has a slope of 1/4. And what do we know? At -2, 1, that will also have a slope of 1/4. And then if I come up here, which is the coordinates of that is 2, 2, if I plug in 2 for x, 2 for y, the slope becomes 1/2. So it will be a little steeper than that. Right, so remember, these are just kind of sketches, right? I'm just trying to get this. So this has to be a little twice as steep as that, right? So that's kind of what's happening as I'm moving up. So if x is 2, y is 3, what do I get? I get 3 over 4. So that becomes even a little more steep than that. And then so that's what, and we understand that these are going to have the same slopes of that, right? So that's kind of what's happening here. Now if I move over to x is 3, what happens here? If x is 3, y is 1, I get 1 over 9. So it's close to 0, but it's slightly upward, right? And then if I come over here, and same thing here, right? It'll be slightly upward. Okay, and then if I'm here, then what do I have? X is 3, y is 2. So that'll be 2 over 9. So it will be a little steeper, right? I'm just trying to make sure that I stay consistent with my steepness, but hopefully you guys get what's going on here. And then over here, my x value is 3, my y value is 3, so it'll be 3 over 9, which is 1/3, so it'll make it even steeper, slightly steeper. Okay, so that's kind of what's going on up here. Now, down here, we're doing the same thing, right? Except here, what do I notice? If x is 1, y is -1, what do I get? I get -1. So it's kind of doing the opposite of this. So if x is 1, y is -2 here, what do I get? I get -2, which is even steeper. And if x is 1, y is -3, I get -3, which is even steeper, right? So these slopes now become negative because of my y value. No matter what the x is always going to be positive. So same thing happens here at 1, 2, and 3. So we get something along those lines. Okay? And then what happens if x is 2 and y is -1? We get -1/4. So it's literally the same slopes of these except it's their negatives. So hopefully you're seeing the pattern, and I'm just going to fill this in. But over here, my y values are negative. They're the exact opposites of those guys, which is going to make the slopes the exact opposite. So if I were to kind of grab these slopes and just take their negatives and draw them out at these points, that'll pretty much complete my direction field or slope field. So, and they're the same thing, right? So if I call it direction field or slope field, it doesn't matter. So it looks something like that. That looks something like that. And over here, same thing is happening, except I'm okay. So now with these slope fields that I've drawn, what's the purpose of this? See, we can see what's happening as I move further, like over. Let's look in the upper left hand, and let's look in quadrant 2. What is it that I noticed? Like, see, if I said, hey guys, I have the solution I'm thinking of this differential equation. One point that's on the solution is right here. Okay, so let's pretend that point is on the solution. And remember, what is the solution of this differential equation? It's just literally its antiderivative. Except now, if I tell you, hey, this point is on the solution of this differential equation, can you sketch me the graph of the antiderivative? And the answer is yes, because what are the slopes of these tangent lines telling you? Hey, these are tangents to what? To the antiderivative of dy dx, which is tangents of the solution. So it'll give me an idea. So what are this slope field or the direction field telling me? As I move to the right, these slopes become steeper, and as I get close to x, what does this become? It becomes vertical. So the slope field is pretty much telling, hey, if you start at this point and you're moving to the right, you're going to start moving up. And the further you go to the right, the steeper the slopes become, which means this should be increasing at a faster rate. And then what happens if we move to the left? What do you notice about the slopes of the tangents? They become less steep, or they get closer and closer to 0. So what is this saying? This is going to settle down, and it's not going to decrease or increase at a faster rate. And then as I go towards negative infinity, this is going to approach the x-axis, which the x-axis, what happens? The slopes are zeroing out. So we could see that the solution of this particular differential equation, there's 4 possibilities, right? There's 4 ways we can sketch what's going on. But if the point is given, then we know exactly how it behaves on that side part of the quadrant, right? So if we were told, for instance, our point is here, then obviously our sketch would differ, right? The curve would be more, it would be kind of doing the opposite of this, just be going downwards, right? If we were told, hey, it's up here, there we just have to follow the slopes of the tangent lines to figure out exactly what the curve looks like. So just keep in mind that what is the advantage of direction fields or slope fields? Sometimes we might have a differential equation where we can't literally find its solution using separation of variables, where there may be more complex ways of doing this, which that's why there is a separate class of differential equations. But then we might say, well, I want to know what its solution looks like. See, if I have some information about its antiderivative, like at least one point, then I could draw a direction field and get an idea as to what the graph of the solution looks like. And that's kind of the advantage here. We can use direction fields to kind of get a general idea as to what the graph of its antiderivative looks like, or how the solution behaves. Okay, so this pretty much wraps up the idea of direction fields. If you have questions, don't hesitate to reach out. I'll be more than happy to clarify any questions you may have.